Next, we're going to be looking at the factors affecting chemical equilibrium. We've been discussing, we've been talking about the various factors that affect the equilibrium position of a chemical system or a chemical reaction. So now we're going to see those various factors and how they affect the equilibrium position of various chemical reactions. Now, the first one we have here is temperature. We're going to look at the effects of temperature, the basic idea of how temperature affects equilibrium system according to Le Chatelier's principle, and also what happens when temperature is increased, when temperature is decreased. And we're also going to look at the types of reaction based on when heat is evolved and when heat is absorbed by a chemical system. So the basic idea of temperature being a factor affecting chemical equilibrium is what happens when temperature is increased and when temperature is decreased. Now, temperature is increased, of course, by addition of heat energy. When you heat the system, the temperature of the system or the temperature of the solution in question or whatever you are heating increases. The temperature increases when you add more heat. So, from the basic idea we have here, it says when temperature is decreased, equilibrium shifts to neutralize the cooling effect by releasing more steam. So when you decrease, when you take out temperature, in this, the first scenario we have here is when temperature is decreased. When you decrease temperature, either by freezing or allowing it to cool, what happens is that equilibrium position has to shift in order to neutralize that cooling effect. Because looking at it critically, let's say you've heated a beaker or a container with water, and as you've heated it, you probably leave it outside to cool. Now, or you put it in a refrigerator, as the case may be. Now, when allowing it to cool, in order for equilibrium to be maintained in that water, that beaker containing water, what will have to happen is that the equilibrium will have to shift so that more water won't be cooled than what is remaining in the container containing the water. So as we have here, equilibrium will shift to neutralize the cooling effect by releasing more steam. Now, when you are cooling something, there will have to be a kind of equilibrium. If you observe, when you bring out when you bring a stove, let's say a pot of water from the fire, and you, let's say, pour some on the floor, or you just pour some on any surface, you see that a lot of heat is going to be liberated. The reason is because equilibrium has to remain in that water so that you won't have more steam evaporating than what is left, and you won't have more of what is left there than what is evaporating. So you are going to have a kind of balance in the system, and for you to have that kind of balance in the system, you see that since the system is cooling, you notice a kind of increase in the rise of steam, so that system will remain in equilibrium. So as the steam increases, it stabilizes the system. So you won't have more of steam or more of one of the variable than the other one. And then the other idea here is when temperature is increased, equilibrium shifts to neutralize the heating effect by absorbing more heat. Now, when you have, using water as an example, heating of water, say in a pot or a jug, a metallic jug, when you increase the temperature, you are going to have a lot of reactions happening. You could have boiling, you could end up having evaporation, the conversion of the liquid into vapor, trying to escape into the atmosphere. But the Chatelier's principle makes us understand that when the temperature is increased, the equilibrium position is going to shift to neutralize that effect, that addition of heat that is taking place, in order for the system to remain equal, to remain balanced, so you don't have more of one of, let's say, steam than what you have of water. The equilibrium is going to shift by allowing the system to absorb more heat. So when you have absorption of heat, you see that there will be a kind of steady of steady balance in what you have as the liquid. Then we're going to look at the types of solutions, the types of reactions rather. You have, when considering temperature as a factor that affects chemical equilibrium. You have endothermic reaction. Now, the word endo means absorption, collecting, taking in. That's what the word, the prefix endo stands for. And then you know that thermic, anything thermic is derived from thermal, which has to do with heat or addition, just heat generally, heat energy. Any concept of heat can be described as thermal. So when you have endothermic, when you fuse those two together, you have endo, which means intake, and thermic, which means heat. So you have intake of heat and you have reaction. So an endothermic reaction is basically a reaction that involves the absorption or the taking in of heat by the system. And as you're written here, heat is absorbed in an endothermic reaction. Now for an exothermic reaction, exo means liberation, giving out. And as we said earlier, thermic means heat. So reaction, exothermic reaction is a reaction in which heat is given off or heat is liberated, in which heat, as the reaction is taking place, you have heat escaping from the system. Now, let's take a look at this example of an endothermic reaction. For this example of an endothermic reaction, you have nitrogen gas and oxygen, also gas, reacting to give you this compound, which is nitrogen 2 oxide. Now, this reaction is basically an endothermic reaction where heat needs to be accompanied with the nitrogen and oxygen in order for you to have the nitrogen 2 oxide formed. Now, we're going to look at what happens when you increase the temperature of an endothermic reaction. Now, from what we have here on the board, I've represented addition of temperature by plus T, where T stands for temperature. You have temperature increasing. Now, fitting right here to represent equilibrium shifting to the right, and forward, meaning the forward reaction is favored by the shift in equilibrium. Now, equilibrium shifting to the right, when you have an endothermic reaction occurring, the equilibrium will shift to the right, which is the side of the product. Facing this way, this is your right. It will shift to this part, which is the right hand. The equilibrium will shift from this reactant side to the product side, and then the forward reaction is going to be favored. The forward reaction will occur, much more. We are going to have, just like we had here, as when temperature is increased here, equilibrium will shift by absorbing more heat. So just as we have the same thing here, in an endothermic reaction, the equilibrium is going to shift to the right side to enable more absorption of heat, so that you have products forming, and so that you won't have, so that when the temperature is increasing here, you won't have, let's say, depletion of the reactants, or let's say production of more products in a way that it's not supposed to be. So for that equilibrium to remain, for you to have this reversibility, this reverse equation occurring side by side and in equal ratio that it's supposed to occur, the equilibrium is going to shift to this side to enable you, so that when you are adding more heat to this one, you have the same or equal, proper volumes of the product being formed as the equilibrium is, as the temperature is increasing. And then I've written minus T here, which means decrease in temperature. Now, for the decrease in temperature, you have left, which means the left side being favored. That is the reactant side being favored. And then backward, which means the backward reaction, which is the combination of this back to its constituents of nitrogen and oxygen being favored, and the equilibrium shifting to the left. So what this is of the idea that when you have when you take away heat, when you try to cool or reduce the temperature of an endothermic reaction, you are going to have the equilibrium shifting to the left. When you are trying to decrease the temperature, that's not what usually happens because it's an endothermic reaction. It takes in heat. But when you are trying to decrease the temperature by taking out heat from this system, the equilibrium is going to shift back to this, to the reactant. So you can have the backward reaction occurring much more freely. It's going to favor the backward reaction. So the backward reaction is going to occur in a fluid way in order to give you this reactant back. So that's what happens when you decrease the temperature in an endothermic reaction. On the other hand, when looking at the exothermic reaction, for that of the exothermic reaction, we are going to look at the example of when nitrogen, which is a gas, reacting with hydrogen gas also to give you ammonia, 2 moles of ammonia. Now, just as I've written here, we're going to see what happens when you increase the temperature and what happens when you decrease the temperature. Now, for when you increase the temperature, I've written here left. Now, for an exothermic reaction which liberates heat, what happens during the reaction is that heat is liberated. Take, for example, I'm going to use a bomb for an example. Now, the chemical reactions that occur in a bomb, basically in some kind of bombs, or most bombs, I would say, is exothermic reaction. So what happens is that you have great heat liberating to the extent that it will cause explosions. Heat, great amount of heat amounts to fire, basically. So you have great amounts of heat being liberated from the chemical reaction that takes place within the chamber, within the bomb container. Then that heat being liberated, causes a kind of expansion of what is left of the bomb. So that's basically the concept of an exothermic reaction, where you have heat being liberated. Some reactions liberate greater amount of heat than some other reactions do. But for this reaction, we are going to see what happens when you increase the temperature. Now, when you increase the temperature of an exothermic reaction, the equilibrium is going to shift to the left, which is the reactant. The equilibrium will shift to the reactant, and then the backward reaction will be favored. This is so because this is not how the reaction is supposed to flow. It's not supposed to absorb heat. But by making it to absorb heat, you have altered one of the properties that is keeping this reaction in equilibrium. And since you have altered it, there has to be a kind of shift in what happens to the backward reaction for everything to remain balanced. Now, in order for everything to remain balanced, once the equilibrium shifts to the left, which is this, it will favor the backward reaction. So when it favors the backward reaction, instead of having much more heat being absorbed by the system than it should have, the backward reaction will ensure that that equilibrium shift will ensure that you have an exothermic reaction still happening in order for this to be kept in equilibrium. Now, for when heat is lost, when temperature is being reduced or decreased, as we would say, which is what happens basically in an exothermic reaction. Heat lost is when heat is being given off. Heat is lost when it is given off by the system, which is basically what happens in an exothermic reaction. So we're gonna have the right side, the equilibrium shifting to the right, and then the forward reaction being favored, because this is how the reaction flows. So as you have heat being removed, being liberated as it's supposed to be as a normal exothermic reaction. As more heat leaves, you have the production of this going on normally, keeping this in equilibrium, keeping the equilibrium constant as it's supposed to be.